Good evening, and welcome back to SleepWise. Tonight, we enter a world where the old certainties of physics begin to loosen. The deeper scientists look, the less reality resembles the smooth and orderly picture they once trusted. At the smallest scales, nature may move in packets rather than in a smooth and unbroken flow. What makes this story so beautiful is that it did not begin with something dramatic. No mountain split open, no planet slipped from its course. The revolution began quietly, in laboratories, in careful measurements, in tiny discrepancies that refused to go away. A few old ideas, elegant and trusted, no longer fit the world as neatly as they once had. That is often how the deepest changes begin, not with noise, but with unease, not with certainty, but with a faint and persistent feeling that something important has been missed. By the end of the 19th century, physics seemed almost complete. Newton had given motion its majestic order. Maxwell had woven electricity, magnetism, and light into one of the most beautiful structures in science. Heat, force, and energy appeared to belong to a universe that was lawful, continuous, and ultimately understandable. You can almost feel the confidence of that age. It was a universe of smooth transitions and reliable causes, where energy could be imagined as flowing continuously like water poured from one vessel into another. Nature felt grand, yes, but also composed, patient enough to yield itself, piece by piece, to disciplined thought. And yet, nature has a way of waiting until confidence becomes comfortable before revealing a hidden seam. Tonight, we will follow that seam gently. We will begin in the old clockwork world, where certainty still seems strong. Then we will watch as light and heat begin to misbehave in quiet, stubborn ways. And from that hush of confusion, two figures will slowly step forward. Max Planck, careful and restrained, and Niels Bohr, imaginative and daring. Neither man set out to make the universe stranger, but together, in very different ways, they helped reveal that it already was. If these quiet journeys have begun to find a place in your evenings, and if there is someone else whose mind might rest more easily inside a calm and curious story, I hope SleepWise finds its way to them too. For now, though, there is nothing to do but listen. You do not need to reach for your phone. You do not need to solve quantum theory tonight. You do not need to remember every name or every experiment by morning. You only need to let the story unfold slowly enough that the strangeness becomes gentle. So let the room grow still. Let the day loosen its hold. Let the old, polished universe gather itself around us one last time. Because in a moment, almost without a sound, its smooth surface will begin to shimmer. By the end of the 19th century, physicists felt they were living in a nearly finished world. Not finished in the sense that every detail had been measured, but finished in structure, as though the architecture of nature had at last been revealed. The largest beams were in place. The hidden gears had names. The old darkness had been steadily pressed back by patient minds and equations of grace. For more than 2 centuries, Newton had stood like a giant over this landscape. His laws of motion had shown how apples fall, how cannonballs arc, how planets keep their paths across the dark. The heavens and the earth, once imagined as separate kingdoms, had been joined under the same serene order. Motion could be described, predicted, trusted. Causes led to effects. If one knew enough about a system in the present, it seemed one could know its future as well. Then came the great flowering of the 19th century. Heat, once understood mostly through sensation and firelight, was drawn into theory. Thermodynamics described energy, work, temperature, and the slow drift by which useful motion becomes diffused into stillness. There was something quietly poetic in this, that warmth spreads, that differences soften, that intense things gradually level into calm. Even disorder, it seemed, had its rules. Electricity and magnetism, once mysterious, were gathered together by James Clerk Maxwell into a single magnificent framework. With a few compact equations, he described fields that moved through space and tied together light, charge, and magnetism in one elegant vision. Light itself now appeared as a wave in an electromagnetic field. Nature seemed not only lawful, but beautifully economical, as though beneath all variety there were a few deep harmonies, repeating themselves in different forms. To stand inside this intellectual moment was to feel a rare kind of confidence, not arrogance, but a deep and quiet satisfaction. The world had not become smaller through explanation. It had become cleaner, more coherent, more exquisitely arranged. There were unanswered questions, but they seemed local now. Small, unfinished corners in a nearly completed room. Nature appeared continuous, stable, and mathematically transparent. Space and time provided a smooth stage. Energy flowed in a seamless stream. Matter moved according to laws that did not blink or hesitate. The old scientific dream had reached one of its most polished forms. A universe of continuity, predictability, and deep intelligibility. Few suspected that the trouble ahead would not be a missing ornament on the structure, but a fracture near the foundation. For now, though, the structure still seemed whole. The equations held. The stars moved. Fields rippled through space. Heat flowed. Light shone. And in lecture halls, many of the finest minds in Europe believed they were living near the end of the great deciphering, when nature had all but finished giving up her secrets. The first disturbance arrived not in the movement of planets or the sweep of magnetism, but in something quieter, the glow of heated matter, a stove coil, a lamp filament, a piece of iron in a furnace. When warmed enough, each began to shine. First a dim red, then orange, then a brighter light as temperature rose. It was a familiar sight, known long before it became a crisis for physics. To the scientists of the late 19th century, This seemed exactly the sort of phenomenon their theories ought to explain. Heat had been drawn into thermodynamics. Light had been described as an electromagnetic wave. Matter, energy, radiation, these no longer felt like separate mysteries. They belonged to one lawful world. And so a natural question emerged. If a hot object emits light, how exactly is that light distributed? Careful experiments began to provide an answer. When physicists studied glowing objects or idealized cavities that absorbed and re-emitted radiation, they found that the emitted light followed a definite pattern. The energy was not spread evenly across all colors. At lower temperatures, the emission leaned toward longer, redder wavelengths. As temperature increased, the peak shifted toward shorter wavelengths. The whole curve changed in a regular, measurable way. The trouble was that classical physics could not reproduce it. Some formulas worked reasonably well over part of the spectrum, especially at longer wavelengths, but failed elsewhere. And when theorists pushed the older assumptions to their logical end, the failure became startling. The mathematics suggested that at very short wavelengths, the emitted energy should rise without limit. A heated object, according to this reasoning, would pour more and more energy into the high-frequency end of the spectrum, in quantities that made no physical sense. Reality did nothing of the sort. The measured spectrum remained finite, smooth, and well-behaved. The equations ran toward absurdity. This was not a tiny mismatch to be tidied away with better instruments. It was a sign that something trusted and foundational had begun to slip. The established picture of matter and radiation, so successful elsewhere, was suddenly unable to account for the ordinary glow of hot things. And this was what made the problem so unsettling. It did not belong to some remote corner of nature. Heat and light were everywhere, in furnaces, stars, flames, and warm surfaces fading into darkness. If the theory failed here, then the failure touched something central. A fine crack had appeared in the confidence of 19th century physics. At first, most hoped it was only a technical inconsistency that would soon be repaired. The old framework was too elegant, too powerful, too richly confirmed to surrender easily. But in the warm glow of heated matter, nature was already whispering otherwise. Beneath the surface of classical certainty, something deeper had begun to resist. For the man who would make the first decisive move, none of this felt like an invitation to overthrow the old order. Max Planck was not drawn to rupture, not the sort of mind that delighted in rebellion for its own sake. He was disciplined, restrained, and deeply respectful of the structure of physics he had inherited. If nature was lawful, he believed, then the task of the physicist was to uncover that law with patience, not to dramatize confusion. By temperament, Planck belonged to the world that had been built before the crisis. He admired rigor, continuity, and underlying principle. He did not wish to replace the classical picture with something strange. He wished to save it, or at least preserve as much of it as he could. That is part of what makes his role in this story so quietly moving. The first man to open the quantum door was not a visionary seeking a new universe, but a careful scholar trying to mend a tear in the old one. The problem that occupied him was the spectrum of thermal radiation, the measured pattern by which hot objects emit light. Experimentalists had traced that pattern with increasing precision, and the data were stubborn. The curve had a definite shape. It rose, reached a peak, then fell away. It did not explode into infinity. It did not obey the expectations that classical reasoning seemed to suggest. Nature was calm and untroubled. Theory was the thing in distress. Planck approached the matter with the seriousness of someone who sensed that even a narrow inconsistency could not be ignored. In physics, small contradictions have a way of growing. A theory may seem majestic from a distance, yet a single misfit between equation and experiment can reveal that something essential has been misunderstood. So he worked, not in the spirit of revolution, but of repair. He searched for a mathematical expression that would fit the observed spectrum exactly. This detail matters. Planck did not begin with a sweeping philosophical attack on continuity or determinism. He began with a technical problem, a stubborn curve, and a desire to restore order. He was trying to find the right formula, the one that would bring theory back into alignment with the measured world. In this sense, quantum theory did not enter the story with trumpets. It arrived at a desk in quiet concentration, through calculation, and yet there was already something delicate in the air. To force agreement between mathematics and experiment, Planck found himself considering assumptions he would not naturally have welcomed. He had not set out to remake reality. But reality, patient and unsentimental, was beginning to press him somewhere new. So tonight, as the old certainty softens, it does so in the company of a man who would have preferred not to soften it at all. Planck enters not as a destroyer of the classical world, but as its loyal servant, called unexpectedly to the threshold of something stranger. The step Planck took in 1900 was, on its surface, modest. He was searching for a formula that matched the observed spectrum of a heated body, and he found one. But hidden inside that success was an assumption so unusual that it would slowly alter the foundations of physics. To make the mathematics work, Planck proposed that energy was not exchanged in a perfectly continuous flow. Instead, it came in tiny, discrete amounts. This was the birth of quantization. The word itself would come to carry immense weight, but the underlying image is simple enough to hold in the mind. Classical physics had treated energy rather like a smooth stream, something that could be divided and varied without limit. Planck's new proposal suggested something else. At least in the processes he was analyzing, energy seemed to be handed over in little packets, in fixed portions tied to frequency. Not any amount whatsoever, but certain allowed amounts. The idea was strange, because it interrupted a habit of thought that ran very deep. A slope may be climbed continuously. A dimmer switch may turn gradually. Water may seem to pour in an unbroken flow. The older imagination of physics favored this kind of smoothness. Nature in that picture did not need to hesitate. It could vary by any tiny degree. Planck's proposal introduced thresholds. It suggested that somewhere beneath the seeming continuity of experience, there might be a more granular order. Even so, Planck himself did not immediately treat this as a complete philosophical break. He did not rise from his calculations announcing that reality had become discontinuous in its essence. The new assumption was, at first, a way to secure the correct result. He had found the formula. He had restored agreement with experiment. The radical meaning of what he had done was not yet fully embraced, perhaps not even by him. That hesitation is part of the beauty of this moment. Great shifts in knowledge do not always arrive with full self-awareness. Sometimes a mind reaches the right answer before it understands how far that answer will travel. Planck had introduced a constant of nature, now known as Planck's constant, and with it a tiny unit that seemed to set the scale of this hidden graininess. The quantities involved were extraordinarily small, which is why the ordinary world still appeared smooth. At human scales, continuity survived as an appearance, but far beneath the surface, something else had begun to show. Nature, it seemed, might not be perfectly seamless after all. Energy might come not as an unbroken wash, but in steps, not as an endless sliding scale, but in little measured gifts. A door had opened, though only slightly. Planck stood at the threshold, still facing the old world, still hoping perhaps that the opening would not need to widen. But the idea was now present, quiet and irreversible. Reality had acquired a grain. What Planck had introduced was more than a useful trick inside an equation. It asked for a slower kind of attention. If energy came only in tiny allowed portions, then the deep fabric of nature might not be smooth in the way physicists had long imagined. The old picture had offered a universe of seamless variation, where quantities could change by any amount at all, however small. Now there appeared the possibility of steps, thresholds, little indivisible acts. It is worth pausing here, because this is the point at which quantum theory first begins to feel less like a calculation and more like a change in atmosphere. In daily life, the world seems continuous. Dawn brightens by degrees. Water pours in an unbroken stream. A violin note can rise or fall so gently that the ear barely notices the motion. Classical physics had taken this smoothness and treated it as a clue to the structure beneath appearances. Nature, it seemed, could slide continuously from one state to another. Quantization suggested otherwise. At least in certain exchanges, nature did not merely slide. It selected. It admitted this amount, but not that one. It moved by permission, by tiny allowed increments, as though beneath the flowing surface of experience there lay a hidden staircase too fine for ordinary senses to detect. The image is not exact in every respect, but it captures something essential. A ramp had become, at depth, a stair. This did not mean that the visible world suddenly lost its grace. The moon still rose gently. Heat still spread across a room. Light still washed over wood, skin, water, and stone. Continuity remained the language of ordinary experience. But Planck's constant was so small that the grain of reality stayed concealed at human scale, much as individual grains of sand disappear when viewed from far enough away. What seemed smooth could still be made of parts. And this possibility carried a quiet, philosophical force. If the most basic exchanges of energy were not infinitely divisible, then the old dream of complete continuity had been softened at its base. Nature was still lawful, still exquisitely ordered, but perhaps not in the way 19th century physics had assumed. Beneath the flowing surface there might be measure, discreteness, and limit. Planck himself did not linger long in this metaphysical mood. He had solved a problem, and in one sense that was enough. Yet the idea remained, and ideas of this kind do not stay politely in the corner where they were first invited. Once admitted, they begin to cast their light elsewhere. So the new strangeness waited there, small and almost modest, like a seed in dry ground. It did not yet seem to demand a new universe, but it had already made the old one less seamless than before. And once a mind has glimpsed grain beneath apparent smoothness, it can never quite return to the earlier innocence. From there, the unease began to spread. What had first appeared as a specialized problem about thermal radiation no longer looked so easy to contain. The deeper one looked, the harder it became to believe that Planck's strange little packets belonged only to hot cavities and laboratory curves. The trouble seemed to reach beyond one technical corner of physics, touching light itself. For much of the 19th century, light had seemed gloriously settled. Thomas Young and Augustin Fresnel had shown the power of the wave picture through interference and diffraction. Maxwell then gave that picture majestic theoretical form. Light was understood as an electromagnetic wave, a rhythmic disturbance moving through space with lawful beauty. This view explained so much, and explained it so well that it carried the authority of truth. To doubt it would have felt almost perverse, and yet nature was beginning to whisper that the wave picture, though profound, might not be complete. The world of radiation was not behaving as though continuity alone could describe it. The spectrum of heated bodies had already hinted as much. Planck's quantized assumption had repaired the mismatch, but it also left an unsettling aftertaste. Why should energy exchange come in packets at all if waves alone told the whole story? This is one of the soft turning points in the history of science. The moment when a concept stops looking like a local patch and begins to feel like a clue. No single experiment had yet swept away the old understanding in one dramatic gesture. The transition was slower, more human than that. A few anomalies here, a few stubborn facts there, and gradually the confidence of an age began to loosen. The wave theory of light was not false in the simple sense. It continued to describe many phenomena with astonishing power, but the new evidence suggested that it might be partial, that beneath or alongside its truth there might be another aspect of light not yet fully named. The old hope that one elegant framework had captured everything was becoming harder to sustain. This is often how a scientific world changes. First there is a difficulty, then a provisional fix, then the uneasy realization that the fix points beyond itself. What once seemed like one narrow inconsistency begins to reveal a broader tension between theory and reality. The old language still works in many places, yet it no longer feels complete. So physics entered the early years of the 20th century with a new fragility in its confidence. Light, the very thing that had seemed so beautifully understood, was becoming restless again. Its wave nature remained undeniable. But somewhere within that familiar radiance, something sharper and more particulate seemed to be waiting, not yet fully seen, but already altering the questions physicists were able to ask. Among those who sensed that the trouble ran deeper was Albert Einstein. He appears in this story not as its emotional center, but as a clear and penetrating witness. Someone willing to take Planck's strange hint more seriously than many of his contemporaries were prepared to do. In 1905, while still a young patent clerk, he turned toward a phenomenon called the photoelectric effect and found in it another quiet fracture in the old order. The effect itself was simple to describe. When light shines on certain metal surfaces, electrons can be released. Classical wave theory seemed to suggest a straightforward expectation. If light is a continuous wave, then brighter light should deliver more energy, and given enough intensity, electrons ought eventually to be shaken free. One might imagine energy building up gradually, the way a swing rises higher with repeated pushes. But experiments did not behave that way. In many cases, increasing the brightness of light did not solve the problem if the light's frequency was too low. Dim light of the right frequency could release electrons, while bright light of the wrong frequency could fail. More striking still, the electrons were emitted without the delay one would expect if energy were being slowly accumulated. It was as though the light arrived not merely as a spread-out wave, but in concentrated acts. Einstein's proposal was daring in its simplicity. He suggested that light itself could sometimes be treated as if it came in discrete quanta, later called photons. Each quantum carried an amount of energy tied to its frequency. If that amount was large enough, an electron could be liberated. If not, no increase in overall brightness would compensate. The crucial factor was not just how much light arrived in total, but the energy carried by each packet. This did not erase the wave nature of light. Interference and diffraction still stood. The beauty of Maxwell's theory did not simply dissolve, but the old wave-only picture had become harder to defend as complete. Light now seemed to possess a dual aspect. Under some conditions it spread and interfered like a wave. Under others it struck matter as though it were particulate arriving in tiny, indivisible units. For many physicists, this was deeply uncomfortable, A wave was one kind of thing, a particle was another. The mind preferred such categories to remain distinct. Yet experiment, calm and indifferent to philosophical preference, was pressing them closer together. Einstein had not solved the mystery of light. He had made it impossible to ignore, and so the strange idea widened. Quantization was no longer confined to the bookkeeping of thermal radiation. It had entered the behavior of light itself. The old certainty that one could choose a single intuitive image for nature was beginning to fail. Physics was moving into a world where familiar categories still functioned, but no longer ruled alone. As this new uncertainty gathered around light, another long-standing question returned with fresh force: the question of the atom. For centuries, thinkers had imagined that matter might be made of tiny, indivisible units. The idea went back to ancient philosophy, but for a long time it remained more suggestion than proof. By the late 19th century, however, atoms had become difficult to deny. Chemistry, especially, had given them a practical kind of reality. Elements combined in fixed ratios. Reactions followed regular patterns. The periodic table, with its elegant recurrence of properties, hinted at an underlying order in matter itself. Atoms were becoming not just philosophical possibilities, but useful explanatory tools. Further evidence from kinetic theory, Brownian motion, and the behavior of gases made the atomic view harder to dismiss. Matter appeared to be built from discrete units, after all, and yet the inner life of the atom remained obscure. If atoms were real, what were they actually like inside? How were their parts arranged? What held them together? These questions grew sharper as experiments probed deeper. J. Thomson's discovery of the electron in 1897 revealed that atoms were not indivisible after all. Something smaller lived within them. Later, Ernest Rutherford's work suggested a dense central nucleus with electrons somehow associated around it. The atom had acquired structure, but not stability. That stability was the problem. Under classical electrodynamics, an electron moving around a nucleus should radiate energy continuously. A charged particle in accelerated motion was expected to lose energy, and if it lost energy, its orbit should shrink. The electron ought to spiral inward and collapse into the nucleus. Matter, in other words, should not remain matter for very long. The ordinary solidity of the world seemed to rest on a model that destroyed itself. At the same time, atoms emitted light in sharp, specific lines rather than in a smooth blur of all possible colors. Hydrogen, for example, displayed a neat pattern of spectral lines, each at a precise wavelength. Why should atoms glow in such exact notes, like an instrument playing only certain tones? Classical physics offered no satisfying answer. If electrons moved freely under ordinary laws, the emitted radiation should have been far less disciplined. So the atom stood at the meeting point of several difficulties. Matter seemed to be built from discrete units. Those units contained smaller parts. Those parts, if governed only by classical rules, appeared unstable. And the light atoms emitted came in exact signatures that hinted at hidden order. The old world was becoming hard to maintain, not because it had failed everywhere, but because it was failing where physics most wanted clarity, in light, in matter, in reality itself. The atom, once a symbol of solidity, had become a new chamber of mystery. Into this changing world stepped Niels Bohr, and he felt different from Planck almost at once. Where Planck had moved with caution, trying to rescue as much of the old structure as possible, Bohr seemed more willing to inhabit an unfamiliar landscape before its paths were fully mapped. He was younger, more audacious in temperament, and more prepared to accept that the microscopic world might not obey the intuitions shaped by ordinary experience. This did not mean he was careless. Bohr could be exacting, subtle, and deeply serious. But there was in him a willingness to remain near paradox, to let contradiction breathe a little longer before forcing it back into familiar forms. In that sense, he became one of the great interpreters of the new physics, not merely because he proposed models, but because he learned how to think inside strangeness without immediately trying to smooth it away. He arrived at a moment when the atom was demanding explanation. Rutherford's nuclear model had concentrated positive charge into a tiny, dense center, which was a powerful advance. But it also sharpened the problem of stability. Why did electrons not collapse inward? Why did atoms radiate in precise lines rather than in a continuous wash? The old laws described many things magnificently, yet here they seemed to generate disorder where nature displayed form. Bohr's genius lay in taking the emerging quantum idea and carrying it into the atom with a boldness that Planck himself had not shown. If energy exchange came in discrete amounts, perhaps atomic structure did as well. Perhaps the electron was not free to occupy just any orbit whatsoever. Perhaps only certain states were allowed, and the atom's stability depended on those restrictions. This was not classical reasoning with a small correction. It was a new kind of permission structure built into nature. There is something quietly radical in that thought. The microscopic world might not be a place where every path available in pure mathematics is realized in reality. Instead, nature might choose. It might allow this orbit and forbid that one, admit this energy and exclude another. Law would remain, but it would look less like smooth inevitability and more like selective order. Bohr did not yet possess the full quantum mechanics that later generations would build. He stood at an intermediate stage where intuition, experiment, and daring simplification had to work together. But he had the courage to take the hints seriously. Where Planck opened the door with reluctance, Bohr was ready to step farther inside. And with him, quantum theory began to move from a troubling idea about radiation into a more vivid picture of matter itself. The strange house was no longer only visible from the threshold. Someone had begun to enter it. Bohr's model of the atom was at once simple, elegant, and deeply strange. It kept Rutherford's central insight, a tiny, dense nucleus at the heart of the atom, but it refused to let the electron behave in the fully classical way. In the older picture, an electron could circle at any distance with any energy, following the continuous possibilities of ordinary mechanics. In Bohr's picture, that freedom was gone. Only certain orbits were allowed. This was the decisive turn. The electron did not wander through an unlimited range of paths, choosing any track that mathematics might permit. It occupied specific permitted states, each with its own definite energy. One may picture these states as rings around the nucleus, though the later quantum view would grow subtler than that. For Bohr, the essential point was restriction. Nature, at the atomic scale, was selective. That selectiveness solved something important. If an electron remained in one of these allowed orbits, Bohr proposed, it would not radiate energy continuously and spiral inward. It would simply remain there, stable. The atom, which classical electrodynamics seemed to render impossible, could now endure. Matter no longer looked like a structure forever on the edge of collapse. It acquired a new kind of stillness. To a classical mind, this was unsettling. Why should only some orbits be possible and not others? What physical mechanism enforced these permissions? Bohr could not fully answer that. His model was not the final theory, and he knew it. But it did something theories must do if they are to survive. It made sense of stubborn facts. It provided order where the old picture had generated contradiction. There is something almost architectural about the Bohr atom. Imagine a staircase that only opens at certain landings, a building whose rooms are few but precise. You may stand here or here or here, but not in the spaces between. The smooth spectrum of possibility has been replaced by a pattern of allowed positions. The atom becomes not a blur of continuous motion, but a structure shaped by hidden rules of admission. This was more than a technical patch. It carried forward the same quiet message Planck had uncovered in another domain. Nature, when examined closely enough, did not seem to grant every imaginable degree of freedom. Again and again, it introduced steps, limits, exact allowances. Energy came in packets. Atomic states came in levels. The old seamless picture softened further. And yet, the model also had beauty. It was not chaos, not a surrender of reason, but a more delicate order than physicists had expected. The atom was still lawful. It was simply lawful in a way that ordinary intuition had not prepared the mind to receive. Bohr had taken the quantum hint and built into it a picture of matter that was both surprising and serene, one in which stability came not from continuous motion, but from permitted form. Once Bohr's allowed energy levels were admitted, another strange consequence followed with quiet force. If electrons could occupy only certain states, then they could not drift gradually from one energy to another in the old continuous way. They could not simply slide down a smooth incline. They had to change by steps. This became one of the signature ideas of the quantum world, the quantum jump. The phrase has since traveled far beyond physics, but in its original setting, it referred to something very specific and very unsettling. An electron in one allowed state could move to another allowed state, but the transition was abrupt. There was no stable halfway home, no lingering position between the permitted levels. Nature seemed to forbid the in-between. This asked the mind to accept a new rhythm. In the classical imagination, change was usually pictured as flowing. A planet arcs continuously through the sky. A pendulum swings through every point along its path. Water cools by degrees. Even when motion is fast, it passes through intermediate stages. The quantum jump broke that habit of thought. At the microscopic level, some changes were not smooth traversals, but discontinuous transitions. It is tempting to imagine the electron as a tiny bead literally hopping from ring to ring, but even that image is too mechanical, too familiar. The deeper point is that the atom's possible conditions are discrete, and when the electron changes its condition, the change is governed by those discrete possibilities. A certain amount of energy is emitted or absorbed, and the atom is found in one state or another. The continuity of the old picture has given way to a grammar of exact difference. This was hard to love at first. It seemed to offend common sense, not because it was chaotic, but because it was so exact in an unfamiliar way. The world of ordinary perception had taught generations of thinkers to expect nature to move through every shade between one condition and the next. Quantum theory suggested that in some of its deepest processes, nature did not always paint in gradients. Sometimes it composed in notes. That musical image is useful here. A violin can glide continuously, but a piano offers distinct keys. The quantum world, at least in this respect, resembled the keyboard more than the violin. Not every pitch was available, not every resting place existed. There were permitted values and forbidden gaps, and yet there was a severe beauty in this. The quantum jump was not a flaw in nature, but part of its hidden style. It implied that change itself had texture, that beneath the apparent smoothness of the visible world, reality could advance in exact, measured steps. The old dream of uninterrupted flow had not vanished entirely, but it no longer ruled alone. In the atom, nature had begun to reveal a more granular choreography. Bohr's model would not have mattered for long if it had remained only a clever image. What gave it weight was its power to explain something that had puzzled physicists for decades: the spectral lines of atoms. When elements are heated or electrically excited, they do not emit a continuous smear of color. They produce sharp, exact lines at particular wavelengths, as though each atom were sounding a limited set of notes. Hydrogen offered the clearest example. Its visible spectrum had been measured with care, and the lines appeared in a pattern of striking precision. Classical physics could describe light as a wave and matter as moving charge, but it could not convincingly explain why atoms should radiate only at these special frequencies. Why these colors and not all the others in between? Why such discipline in the midst of microscopic motion? Bohr's answer followed naturally from the quantum idea. If the electron could occupy only certain allowed energy levels, then light would be emitted or absorbed only when the electron moved between those levels. The color of the light would reflect the exact energy difference between one state and another. A larger jump would produce one frequency, a smaller jump another. The atom's spectrum became a map of its permitted transitions. This was a beautiful moment in the history of science, because a strange theoretical proposal suddenly found itself mirrored in precise experiment. The sharpness of the spectral lines no longer looked arbitrary. They became signatures of hidden structure. The atom was not glowing randomly. It was revealing the architecture of its internal energies. One can linger here for a moment because the image is so gentle and so profound. Every element carries its own luminous identity. Under the right conditions, it gives off a distinct pattern of light, like a fingerprint written in color. The new quantum model explained why those fingerprints were discrete rather than continuous. Nature was not pouring out energy in an undifferentiated wash. It was speaking in exact intervals. This gave the new theory something invaluable. Not certainty, perhaps, but credibility, with beauty behind it. Quantum ideas had seemed abstract, even reluctant, when they first arose in Planck's treatment of thermal radiation. In Bohr's atom, they gained a clearer shape. The theory did not merely rescue a calculation. It illuminated a visible phenomenon that experimenters could measure again and again. And so the atomic spectrum became one of the first great pieces of evidence that the microscopic world was governed by quantized order. The lines of color, once mysterious, now looked like windows into nature's hidden staircase. Each line marked a difference. Each difference implied a level, and each level suggested again that the deep world was made not of seamless continua, but of selected forms and measured steps. By this point, quantum theory could no longer be dismissed as a narrow remedy for a peculiar problem in heat and light. It had reached too far. It had entered radiation, light itself, atomic stability, and the patterned colors emitted by matter. What began as a local inconsistency was becoming a new framework for the microscopic world, not yet complete, not yet fully understood, but increasingly unavoidable. This widening did not happen all at once. There was no single evening when physicists laid down classical thought and awoke fully quantum the next morning. The shift was slower, more hesitant, and more human than that. Old ideas continued to work magnificently in many domains. Bridges still stood. Planets still moved as Newton said they would. Waves still interfered. Electricity and magnetism still obeyed Maxwell's grand equations. The classical world had not been abolished. It had been bounded. That may be one of the gentlest ways to understand the change. Quantum theory did not declare the older physics worthless. It revealed its range. At large scales, in ordinary conditions, continuity and determinism remained powerful and often sufficient. But when one passed into the intimate territory of atoms, radiation, and elementary exchange, the older language began to lose its grip. There, nature required a subtler grammar, and the emotional meaning of this was significant. The 19th century had hoped for a unified picture that felt smooth, transparent, and almost complete. The early 20th century was discovering that completeness, if it existed at all, would not look like that. Reality at small scales was lawful, yes, but not always intuitive. It did not necessarily conform to the habits of imagination built from everyday experience. So the frame widened. The quantum was no longer just a packet of energy in Planck's equations or a permitted orbit in Bohr's atom. It had become a signal that the microscopic world might be organized by discreteness, selection, and probability in ways classical thought had not anticipated. Physicists were no longer simply patching isolated failures. They were learning a new style of explanation. This is often the hidden shape of a revolution in knowledge. At first, the change seems technical, then it becomes structural. Eventually, it becomes conceptual. Words that once seemed secure, energy, light, orbit, state, acquire new meanings under the pressure of experiment. Familiar terms remain, but their inner life shifts. And so, softly but unmistakably, quantum theory began to present itself not as an emergency repair, but as the beginning of a deeper account of nature. The world had not become less ordered. It had become more intricate. Beneath the broad calm of classical law there was another order, finer and stranger, waiting to be named with greater care. As the quantum picture widened, more minds entered the scene, each bringing a different tone to the growing transformation. Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger would each help carry the theory beyond the early language of packets and orbits into something more abstract and more powerful. For now, they need not arrive as crowded personalities. It is enough to feel them as part of an approaching wave. De Broglie offered one of the gentlest and boldest reversals. If light, long understood as a wave, could behave in some experiments as though it came in particles, then perhaps matter could show the opposite duality. Perhaps electrons and other particles possessed a wave-like aspect as well. It was a thought of remarkable symmetry. The boundaries between categories were beginning to blur in both directions. Then came Heisenberg, austere and penetrating, willing to abandon familiar visual pictures if the mathematics and the experiments demanded it. In his hands, the theory began to loosen its dependence on little planetary images of electrons circling nuclei. What mattered was not what could be comfortably imagined, but what could be known, related, and predicted. The microscopic world was asking physicists to become less attached to ordinary intuition. Schrödinger, by contrast, brought a more continuous and flowing sensibility back into the story, though in transformed form. His wave equation gave the quantum world a new mathematical voice, one that seemed at first almost to restore smoothness, yet did so in a way that led not back to classical certainty, but deeper into quantum ambiguity. The wave had returned, but it no longer meant what it once had. Taken together, these thinkers widened the atmosphere of the theory. The old oppositions, wave or particle, continuous or discrete, path or hidden state, no longer held as cleanly as before. The quantum world was becoming less like a mechanical model one could hold in the hand, and more like a subtle structure one had to approach indirectly through mathematics, experiment, and disciplined humility. There is a particular mood in this phase of the story. Physics is no longer merely surprised, it is being transformed. The first generation had discovered the cracks. The next was learning how to live inside them, how to build new forms of understanding where the old intuitions no longer reached. The atom was no longer a miniature solar system in any simple sense. Light was no longer only a wave. Matter was no longer only a collection of tiny solid bits. The world, at its deepest scale, was becoming more fluid in concept and more exact in law. De Broglie, Heisenberg, and Schrödinger helped make that possible. They belong here not as distractions from Planck and Bohr, but as the widening horizon beyond them. The signs that quantum theory was no passing disturbance, but the beginning of a new intellectual landscape. By the middle of the quantum revolution, the strangeness had deepened beyond packets of energy and fixed atomic levels. Physicists were now being asked to accept something even harder for the classical imagination, that the very categories by which matter had long been understood might need to soften. Particles, under certain conditions, behaved like waves. Waves, under certain conditions, arrived in ways that resembled particles. The old distinctions had not vanished, but they no longer stayed in their assigned rooms. This did not mean that an electron became a little pebble one day and a water ripple the next. The point was subtler than that. When scientists examined the microscopic world, they found that no single everyday image could capture it completely. An electron might produce an interference pattern, spreading its possibilities in a wave-like way, and yet also appear in a detector as a localized event. Light, too, could travel with the elegance of a wave and still strike matter as though it had arrived in discrete quanta. Nature seemed unwilling to fit into the tidy boxes that language preferred. Then there was uncertainty. In classical physics, uncertainty was often a practical limitation. One might fail to measure perfectly, but the world itself was assumed to possess exact values all the same. Quantum theory made a gentler and more unsettling claim. At the deepest level, certain pairs of properties could not both be fixed with unlimited precision at once. Position and momentum, for example, were not simply hidden from us by clumsy instruments. Their exactness was constrained by the structure of the theory itself. This did not turn reality into chaos. It did not mean that anything could happen in any fashion whatsoever. Quantum systems still followed disciplined mathematical laws, and experiments still yielded reliable patterns. But the old dream of perfect predictability, the dream that complete knowledge of the present could unlock the future in full detail, had begun to recede. Probability entered not as ignorance alone, but as part of the grammar of the microscopic world. That shift can be held softly. Imagine mist over a field at dawn. The field is real. The air is real. The light is real. Yet edges do not always present themselves with perfect sharpness. The world has not dissolved. It has become subtler in the way it shows itself. Quantum theory offered something like that to physics. Not a universe stripped of order, but a universe in which order no longer meant absolute classical certainty. And so the strange house widened further. Light and matter were no longer governed by the calm simplicity of old categories. Prediction remained, but in altered form. Law remained, but with probability at its heart. The universe, examined at its smallest scales, had become finer-grained and harder to picture, and therefore, in a quiet way, more wondrous. Something had been lost in this transition, and the loss was felt keenly by many of the people living through it. The old universe of classical physics possessed a kind of clarity for the mind. It was orderly, continuous, and in principle transparent. If one knew enough, one could imagine tracing every motion back to its cause and forward to its consequence. The cosmos seemed like a vast and beautifully made clock, intricate beyond measure, yet fundamentally legible. Quantum theory dimmed that vision. The world at depth no longer appeared as a perfectly smooth mechanism unfolding with complete inevitability. Electrons did not inhabit every possible orbit. Light did not behave only as a wave. Measurement itself entered the story in troubling ways. Probability replaced certainty in places where physicists had hoped for exact foresight. For some, this felt like a surrender, as though science had reached a wall and begun speaking in approximations because it could go no further. But that was not what had happened. The new world was not a retreat into vagueness. It was, in many ways, more disciplined than the old one, because it refused to promise an intuitiveness that nature itself did not grant. Quantum theory did not abandon law. It refined it. It did not dissolve structure. It revealed a deeper structure, one hidden beneath the broad successes of classical reasoning. The loss, then, was not order itself, but a certain comforting style of order, and much was gained. The microscopic world, once riddled with contradictions, began to make new sense. Atomic stability, spectral lines, chemical behavior, and the architecture of matter all came into clearer view. The universe had not become less intelligible. It had become more layered. One had to meet it with greater humility and perhaps with a more patient imagination, but it still answered careful questions with astonishing precision. There is something almost human in that exchange. Childhood prefers clean boundaries and simple causes. Maturity learns that reality can remain lawful without becoming easy, coherent without becoming obvious. Quantum theory brought that kind of maturity to physics. It asked scientists to release certain inherited comforts without giving up on understanding itself. So the deterministic clockwork faded, but not into darkness. It faded into a world more finely textured than before, a world of amplitudes, thresholds, probabilities, and exact relations that did not resemble ordinary common sense, yet proved truer to experiment. The universe had become stranger, yes, but also richer. What replaced the old certainty was not disorder, but a subtler harmony, one that asked more of thought and rewarded it with a deeper form of wonder. At this late point in the story, it is worth returning to the two men who helped guide the opening movement of the quantum age, Max Planck and Niels Bohr. They were not alike in temperament, and that difference matters. Together, they suggest that major changes in knowledge are not carried forward by one kind of mind alone. Some open the door reluctantly, preserving all they can. Others cross the threshold more willingly and learn to dwell where the old certainties no longer hold. Planck was, in many ways, a guardian of order. He did not seek to dissolve the classical world, and he never seemed entirely comfortable with the depth of the break his own work implied. His first quantum was born from restraint, from a desire to restore agreement between theory and experiment, with the least possible violence to established principles. He moved carefully, almost reluctantly, and that caution gave his breakthrough a special dignity. The revolution began not with theatrical rebellion, but with intellectual honesty. Bohr carried a different energy. He was willing to inhabit a world that could not be made comfortable by familiar images. Where Planck had introduced discontinuity in the exchange of energy, Bohr allowed discontinuity to shape matter itself. He accepted that electrons might occupy only certain states, that atomic change might happen in jumps, that explanation at the microscopic scale might require rules that could not be fully visualized in classical terms. He did not merely notice the strange house. He began arranging furniture inside it. This contrast is one of the quiet beauties of quantum history. Planck's greatness lies partly in his hesitation. Bohr's greatness lies partly in his willingness to continue. One stood at the threshold, sober and disciplined, holding on to the old architecture even as it softened beneath him. The other ventured farther inward, exploring how a lawful universe might still exist when continuity, predictability, and visual intuition could no longer be trusted in the old way. Neither man completed the theory. Later thinkers would deepen, formalize, and complicate everything they began. Yet the emotional arc remains clear. Planck opened the door because reality left him no honorable alternative. Bohr stepped through because he sensed that physics could not retreat. Together, they mark two necessary responses to truth: fidelity and courage. And perhaps that is why their presence still feels so calming in a story this strange. Quantum theory did not emerge from chaos or reckless speculation. It emerged from disciplined minds, trying in different ways to remain faithful to what nature was showing them. The passage from the old world to the new was not smooth, but it was sincere. It was guided by people willing to think carefully at the edge of what thought had previously allowed. For all its strangeness, quantum theory did not remain confined to blackboards and philosophical debate. It moved quietly into the practical world, and there it proved astonishingly fertile. The modern age, in ways most people rarely pause to consider, rests upon quantum foundations. The theory that once seemed to threaten common sense now helps sustain the ordinary devices through which daily life unfolds. Consider the semiconductor. Its behavior depends on the quantum structure of electrons in solids, on allowed and forbidden energy bands that determine whether a material conducts, insulates, or occupies the subtle middle ground in between. From that understanding came the transistor, and from the transistor came the dense electronic architecture of modern civilization: computers, smartphones, data centers, communication networks, and much of the quiet machinery of contemporary life. Lasers, too, are children of the quantum world. Their precise beams arise from carefully managed electronic transitions, from atoms and molecules releasing light in coordinated ways that classical intuition alone could not have predicted. What once appeared as an abstract idea about energy levels became, in time, a tool for surgery, measurement, manufacturing, communication, and countless forms of delicate control. Chemistry, at its deepest level, also belongs here. The shapes of molecules, the strength of bonds, the behavior of electrons shared between atoms. All of these are illuminated by quantum principles. The softness of water, the rigidity of diamond, the reactivity of oxygen, the pigments of leaves, and the folding of proteins all rest on microscopic laws far stranger than their calm outward appearances suggest. Even the screens that glow softly in dark rooms, the clocks that keep astonishing time, the medical scanners that peer into hidden interiors, and the solar cells that gather energy from sunlight all carry this inheritance. Quantum theory did not remain a remote interpretation of the world. It became part of the invisible infrastructure of modern existence. And yet, something lovely remains in that fact. The practical success of quantum theory did not empty it of wonder. If anything, it deepened the wonder. The same universe that once startled physicists with discontinuity, uncertainty, and duality turned out also to be generous enough to build with. The strange became useful. The mysterious became quietly dependable. So when we speak of modern life resting on quantum foundations, we mean that beneath the smooth surfaces of the everyday world, beneath glass, circuitry, light, chemistry, and signal, there persists that earlier revelation. Reality at depth is quantized, selective, and subtle. The modern world runs, often silently, on the success of minds willing to trust a truth even when it first arrived, wearing the face of strangeness. Now, as the story slows toward rest, we can return to the image with which the evening began. the scientific dream of a smooth and fully continuous universe. It was a beautiful dream, and in many ways a fruitful one. It gave humanity laws of motion, fields of light, engines, bridges, astronomy, and an immense confidence that the world could be understood through reason. Nothing in the quantum story requires us to mock that inheritance. It was a noble way of seeing, and it still speaks truly across much of the visible world. But at greater depth, the universe turned out to be more finely textured than that dream had imagined. Energy came in packets. Atoms admitted only certain states. Light and matter refused to stay within single categories. Uncertainty entered where perfect foresight had once been expected. Probability moved inward, not merely as a confession of ignorance, but as part of the world's deep structure. The polished surface of classical certainty did not shatter into nonsense. It became translucent, and through that translucence a different beauty appeared. Reality was not less elegant for being granular. It was not less worthy of trust for being probabilistic. It was, if anything, more astonishing. A cosmos in which law and mystery were companions. Beneath the seamless appearances of daily life, there existed a subtler order, one composed of exact relations, hidden thresholds, and finely measured possibilities. Perhaps that is one of the gentlest lessons quantum theory offers. The universe does not owe us intuitiveness. It does not have to resemble the habits of thought formed by bodies moving at ordinary scale through ordinary light. And yet it remains deeply knowable. It answers careful experiment. It yields precise mathematics. We are not exiled from truth by its strangeness. We are invited into a humbler kind of intimacy with it. So tonight, we leave the great clockwork halls of classical certainty and step, softly, into a quieter chamber. Here, the world is textured, granular, and probabilistic at its roots. Here, change may come in jumps, light may arrive in packets, and matter may carry the behavior of waves. Here, the foundations of modern life hum invisibly beneath screens, circuits, chemicals, and stars. And here, perhaps, wonder deepens rather than fades, because the universe has revealed that it is more subtle than the waking mind first assumed. The world slows, and so do we. The questions that once seemed sharp begin to soften. The mind that followed Planck to the threshold and bore a little farther into the strange house beyond it can now let the house grow quiet. The atoms remain in their hidden patterns. The photons continue their patient journeys. The laws of nature go on in silence, and somewhere beneath sleep, beneath memory, beneath language itself, the universe keeps its delicate measures, not less beautiful for being stranger, but more so. Good night.